Hello, everyone. Welcome to the Wednesday live stream from Chem Help ASAP. So in today's live stream, we are going to be continuing with our topic of equilibrium, but this time we are going to be talking about heterogeneous equilibrium. And we're going to do a couple of different kinds of problems. We're going to talk about how to write your K for heterogeneous equilibrium. Then we're going to do some calculations with it, and we're going to bring in some other topics as well as we talk about heterogeneous equilibrium. Okay, so with that being said, of course, let's just go ahead and jump into our first problem. All right, so we have arsine gas, that's ASH3, decomposes according to the following chemical equation, and we are given a balanced chemical equation right here. Okay, so pure arsine was placed in a sealed vessel at 392 torr and allowed to achieve equilibrium. Okay, after equilibrium was reached, the pressure in the flask was found to be 488 torr. And so we need to calculate the equilibrium pressure of the hydrogen gas, and we also need to find the value for Kp for this reaction. Just as an aside, this is Kp because we're dealing with pressures as opposed to Kc, which would deal with concentrations, although Kc is often called K. Or you might even find Keq, which is just an equilibrium constant. Now, this is an example of heterogeneous equilibrium because if we go back to this chemical equation, you can see we have two gases and a solid. So we have a mixture of states here. Now, when we talk about Kp, that is only for gases. So when we write the Kp for this reaction, which let's just go ahead and write the Kp for this reaction, we only include the gases. So let's even just, I'm going to write it over here on the left. So whenever you write a K, of course, it's products over reactants, but we are going to omit our solid, in this case, our arsenic. So it is simply going to be our hydrogen gas cubed over our arsine gas squared. Although, really, I've put brackets around these. These should be pressures, not brackets. Brackets denote concentration, and these are pressures, not concentration. Okay, but that is still, it's going to be the pressure of our hydrogen gas cubed over the pressure of our arsine gas squared. Again, the cube simply comes from the stoichiometric coefficient, and the squared, again, comes from the stoichiometric coefficient. So that is the expression for our Kp, and this question does ask us to calculate the value for Kp, so we will get to that. But we can't actually do that quite yet because we need values for these pressures for hydrogen and for arsine. So what I want to do first with this problem is I want to set up my ICE or RICE table, however you think about it. I'm actually going to take this equation and I'm just going to rewrite it so it works with my table. Okay, so I'm going to start over here on the left. So I am just rewriting my balanced chemical equation. Okay. H2. All right, so now my initial amounts I started with 392, oops, sorry, I didn't mean to make a mark there, 392 torr of arsine. So I'm going to put 392 right here, and I have 0 product. So the nice thing about this problem is because you've only started with reactants and you have no products, there's no need to calculate Q to figure out which way the equilibrium is going to shift, because it is most definitely going to shift to the right. The question is, how much is it going to shift to the right? Okay, so those are my initial, we won't say amounts, we'll say those are our initial pressures. Again, we're dealing with gases here. Now our equilibrium, again, we know is going to shift to the right. So that means I'm going to have a negative 2x on my reactant side, and then this is going to be 2x, and this is going to be 3x. That is my amount consumed or formed in the case of the products. So now I just add down my columns for my equilibrium pressures. Okay, so this is just simply going to be 392 minus 2x. This is 2x. And this is 3x. So now I can take my equilibrium pressures that I have here and plug it into my Kp. Okay, so Kp is then, again, my hydrogen. Yes, I wrote that as concentration, but its pressure is going to be 3x. Again, the 3x just comes from here, and that is going to be cubed. And that is going to be over my arsine right here, 392.0 minus 2x, and that is squared. Now, I did follow through here with my solid. You don't have to, because of course, anytime you have a solid, we just don't include it. So you can even just leave this column totally blank, and that is completely fine. All right, so now we have our expression for Kp with our expressions for our equilibrium pressures, but we have a problem here because I have two variables and one equation. So I don't know my Kp. That's actually something I'm going to try and calculate. And I also don't know my value for x. So at this point, I'm kind of stuck. I need to bring in another value here, right? Okay, so I'm guessing because the question asked me to calculate Kp that I cannot figure out Kp quite yet. So I'm going to focus in and can I figure out what x is? Well, there is a piece of information that I haven't used yet, and that is the pressure in the flask was found to be 488 at equilibrium, or when equilibrium was achieved, or it says when equilibrium was reached. So that is going to be my piece of information that is going to give me my value for x. So the thing we need to remember here is we're dealing with gases. And so remember that the pressure in the flask is going to be the pressure of all of our gases added together. This is Dalton's law of partial pressure. So my total pressure in the flask at equilibrium is going to equal the pressure of my acetine plus the pressure of my hydrogen gas. All right. Again, this is at equilibrium. I know what this total pressure is. It's right here. That is the total pressure. So I can put in 488 torr for this pressure. And while I don't have exact numbers for my pressure yet for acetine and hydrogen, I do have expressions for that, right? I've got my expressions from my ice table right here. So let's plug those pressures in. So my pressure for acetine is my 392 minus 2x, plus for hydrogen is just 3x. And now I have a second equation, and you can see this second equation using Dalton's law of partial pressures. I can solve for x. This is actually pretty easy because, of course, negative 2x and 3x just gives me x. So on the right-hand side, this is going to simplify very nicely. 2 plus x, which means my x is equal to 96 torr. Okay, so that's fantastic. We know what x is, which means we can calculate the equilibrium pressure of hydrogen gas. We can calculate our equilibrium pressures for everything. So our equilibrium pressure for hydrogen gas, so let's call this pressure of hydrogen, is equal to 3x. Again, this is just from our ice table, but we know what x is, so this is simply 3 times 96 torr. And that value is 288 torr. And let's go ahead and calculate our pressure for our acetine gas. Again, we have our expression right there. So our pressure SH3 is equal to 392 minus 2x. So if I'm going to plug in x here, that's 2 times 96. Yes, that is torr. And so my pressure of my acetine is 200 torr. Okay. So now I have answered the first part, my calculate equilibrium pressure of hydrogen gas, and then I need the value of Kp. And this is kind of why I went ahead and calculated my pressure of acetine, because I'm just going to plug into my Kp. Let me just switch colors so it's a little more obvious. Okay, so my Kp, I will rewrite this with proper pressures, is my pressure of my hydrogen gas, and that is cubed over the pressure of acetine, and that is squared, and I have those values. So Kp is going to be my pressure of hydrogen, which is 288 torr cubed, over the pressure of my acetine, which I have also calculated down here. That is 200 torr squared. So when you put that in your calculator, you are going to get 597. And let's see, this is going to be torr cubed over torr squared. So that is just going to be units of torr for Kp. And those are the two parts of this question that I wanted to answer. So a lot of times in these kind of problems, we get very used to in equilibrium problems always solving for x using the ICE table, and we're used to having a value for k, but you don't always have a value for k. So if you get stuck, like we were stuck right here with Kp and our x, go back to the problem, reread it. There's going to be an extra piece of information that is most likely going to help you find x, and then you can calculate whatever your k is. But that's kind of a common place for students to get stuck. Okay, that was our first problem. No questions. So let's go on to our next problem. Let me switch back here. Okay, so sodium bicarbonate decomposes according to the following reaction, and we are given a chemical equation that is not correctly balanced. Let me do that really quickly. There should be a 2 in front of there. I'm sorry, that is my typo. I did not transfer this over properly. Okay, so here is now our balanced chemical equation. At 125 degrees Celsius, Kp equals 0.25 atmosphere squared. In a 1 liter vessel, we've got 10 grams of bicarb is heated to 125. Okay, so that's good. So our Kp temperature is the same temperature that we're running the reaction at. If it is not, you have to find a new K. Assume the vessel has been evacuated and only contains our bicarb. Okay, that's great. So we don't have to worry about like that it's open to the atmosphere, and then we have a mixture of gases to deal with in the atmosphere as well as our chemical reaction. So that simplifies things. What are the partial pressures of carbon dioxide and water when equilibrium is reached? And calculate the number of grams of bicarb and sodium carbonate when equilibrium is reached. And what would the volume of the vessel need to be in order for all 10 grams of the bicarb to decompose? Okay, well, this last question tells me that obviously I'm not going to get all of them to decompose in my 1 liter vessel. So that's just a little bit of information I'm going to tuck away. So there are a lot of questions to answer in this question. And I know right now it doesn't look obviously totally understandable, but don't worry, we will get to this. Again, we are dealing with heterogeneous equilibrium because we have 2 solids and 2 gases. We're also dealing with a Kp, which means we're dealing with pressures only, which means our equilibrium expression will only have our carbon dioxide gas and our water vapor in it, and we do not include any of the solids. So let's just write our expression like we did last time for Kp, just to kind of organize our thoughts. So Kp is simply going to be the pressure of our carbon dioxide gas times the pressure of our water vapor. Now, this is just one thing I want to say as an aside. we're used to water, of course, being at room temperature and being a liquid. If water was a pure liquid, in this expression, we would not include it in our KP. So when you're reading your chemical equations, make sure you're reading these states very carefully because you want to include all of your gases in your KP expression. So it's very easy to just read that it's water and think that it's liquid and not include it in your KP. So just want to put that as an aside there. Okay, so we have our KP, and what I want to do next, just like we did in the previous problem, is set up an ice table. So I'm going to rewrite my balanced chemical equation and get my ice table filled in. Okay, sodium carbonate. Oops, sorry, Na2. CO2 and water. All right, so this is 10 grams. Because it's a solid, I know it's not going to matter, so I'm just going to go ahead and put that in. And we know we have zero product because initially we just put that 10 grams of bicarb. We don't put anything else in. Again, we don't need to calculate Q because we know when there's only reactants and no products, the equilibrium is going to shift to the right. So we can go ahead and write in our consumed. And so that is going to be a minus 2x, and these are all plus x here, which means my equilibrium expressions or pressures are going to look like this. Great. And again, I could have left out these two columns because they are solids. They're not part of my KP at all. Okay, so what I'm going to do is I'm going to plug into my KP. So my KP is just my pressure of CO2, which is X, times my pressure of my water vapor, which is also X. Just call this X squared. Now in this case, we do have a value for KP, so we can calculate what X is. So my value for KP is 0.25 atmosphere squared equals X squared. So of course, X is equal to 0.5 atmospheres, and this is equal again to the pressure of carbon dioxide, which is also equal to the pressure of water. Okay, so these are the partial pressures of carbon dioxide and water when equilibrium is reached. Okay, so now we need to figure out how many grams of my solids do I have left. So I'm going to have to do some stoichiometry, which means I need moles, which means I am going to have to use ideal gas law. Okay, so good old ideal gas law. And specifically, I want to know, I'm going to know the total pressures because I want to know the total number of moles. Okay, so I'm going to change ideal gas law just a little bit here. So I want to be really careful because I can't mix in, say, the pressure of carbon dioxide and like our total number of moles, or the total pressure and just say the volume of water. So I need to make sure that if I'm talking about the total pressure, it means I'm talking about the total volume, which means I'm talking about the total number of moles times R times T. So be really careful that you don't accidentally mix and match your units, that we're talking about our total numbers, our pressure, volume, and moles, because that is what we know. So we only know, and especially what drives this is our volume. We only know our total number of volume. Like I cannot tell you what the volume of carbon dioxide or water vapor is, but I do know the total volume of the vessel. So I'm going to have to use total pressure, total volume, total number of moles. Okay, again, I know my total volume, so I'm going to have to calculate my total pressure here. So let's maybe do this as a little bit of a side calculation. So my total pressure, again, this is Dalton's law of partial pressure. That is going to equal the pressure of my carbon dioxide plus the pressure of my water vapor. Now, the great thing is we know those pressures, they are both the same. These are both 0.5 atmospheres. So my total pressure is equal to 1 atmosphere. Okay, that's going to make my math really easy. I like that. Okay. Again, I know my total volume because it's in a 1 liter vessel. And now I need to deal with my total number of moles. There are a couple of ways to do this. Let's use mole fraction because it's a little bit different. And I really want to put this in a different space. But I can't. So let me go back to my green, and I'm going to use this lower right-hand corner. Okay, so if you remember mole fraction, and let's do carbon dioxide. So mole fraction is going to equal my pressure of my carbon dioxide over my total pressure. And so this is going to equal my 0.5 atmospheres. I am squeezed over my total pressure, which I know, which is 1 atmosphere. Okay, so this is really nice. My mole fraction of CO2 is equal to 0.5. That is unitless. But mole fraction is also equal to your number of moles of carbon dioxide over your total number of moles. Okay, so I've got a total number of moles. Oh, I did this. I've kind of done this backwards. I'm sorry. I do want to find my total number of moles using my ideal gas law. So I got a little bit ahead of myself here with my mole fraction, but we will use it. I promise we will use it. Okay, so I calculated my total pressure here, and I didn't finish with my ideal gas law. You know, brains are not working all that well. Okay, so here is my total number of moles. Now for my value of R, this is a little bit messy, so let me rewrite this. I want to make sure that my units are going to cancel. So because this is atmosphere and this is liter, and of course I'll calculate my temperature in Kelvin, I need to make sure I use a value for R that has liters, atmospheres, and Kelvin, and that is going to be probably the value of R that you're most familiar with, 0.8206, and that is liter atmosphere over mole K. That's also another very common mistake that I see is students get used to using one value for R, and so they always use that value for R, and they don't make sure that their units match. And then you are using the right equations, and your method is good, but you have messed up your units, and that's going to give you the wrong answer. Okay, and then I just need to take my 125 and to convert to Kelvin. So that is going to be 398 Kelvin each. Okay, that's kind of squeezed in there. And I have actually plugged this into my calculator, and I have calculated what my total number of moles is. And that is 306 moles. Okay, great. Now I can go back to my mole fraction. It's like my brain got ahead of what I had actually calculated at that point. Okay, so I know my mole fraction, it's 0.5. I got that from my pressures. So now what I want to know is I want to know my moles of, that is CO2. That looked a little odd. But I know my total value of my total moles because I just calculated it with my ideal gas law. So if I'm going to plug this in, I'm going to say 0.5 is equal to my moles of CO2 over my total number of moles, which is right here. And then I can calculate my moles of CO2, and that is going to give me 0.0153 moles. I'm going to have to go to my next page because I am totally running out of space here. All right, but we'll be able to switch back and forth. I'm trying to make sure that I explained the connection here. Why am I going after my moles of CO2? Although you could have gone after your moles of water as well, it wouldn't make a difference. I need to do stoichiometry. So if I can figure out how many moles of carbon dioxide are formed, then I can use that to figure out my moles of sodium carbonate that have formed, and I can also use that to figure out how many moles of my sodium bicarb I used. So now that I have my moles of CO2, what I want to do is I want to do my stoichiometry so that I can then figure out this second part, calculate the number of grams of bicarb and sodium carbonate when equilibrium is reached. But to do stoichiometry, you always need moles. So that's why I was working really hard to get to moles, because I want to do my stoichiometry. Let's rewrite our balanced chemical equations just so we have it at the top of the page, because we're getting ready to do stoichiometry. And balanced chemical equation is key for stoichiometry. Okay, so this is in equilibrium with my sodium carbonate and my carbon dioxide and my water. Okay, these are both solids and these two are gases. All right, great. So my number of moles for CO2, which I just calculated, is 0.0153 moles of CO2. So now I want to do my stoichiometry, and it really doesn't matter which one I go for. Let's do our easier one first. Let's figure out how many moles of sodium carbonate were formed. So I'm going to start with my moles of CO2. Moles of CO2. And now I'm just doing straight up stoichiometry here. So to go from moles of CO2 to moles of sodium carbonate is just a 1-to-1 ratio, which is always nice. CO3. But the problem asked me for grams, I believe. Calculate the number of grams. Okay. So that will give me my moles of sodium carbonate, but I need to calculate grams. So I just need the molar mass to convert. And my molar mass is 105.989 grams of sodium carbonate per mole. And this will give me my grams formed. So this is 1.62 grams of sodium carbonate formed. So a lot of work to do, a pretty easy stoichiometry problem, right? Okay, now we need to figure out how many moles of my sodium bicarb are left. But again, I'm going to use my stoichiometry. So I'm going to start with my moles of carbon dioxide. So using my moles of carbon dioxide, now I'm going to go from carbon dioxide back to sodium bicarb, and that is a 1-to-2 ratio, or maybe you could think of that as 2-to-1. It just depends on how you like to think. If you like to think numerator first, just make sure, of course, that your moles of CO2 cancel here. Again, if you're writing down your units, which you should be, even though I know it's easier just to put the numbers in, it will make sure that you never flip a stoichiometric ratio, which is always so frustrating when you get a ratio backwards. Okay, so that is my moles of sodium bicarb, and I just need to convert to grams because, of course, I am looking for grams. And that is 84.007 grams of sodium bicarb. Okay. All right, so that is going to give me 2.57 grams of bicarb. Okay. Now, the thing to remember here is that is a reactant. So this is not grams of sodium bicarb formed, right? Because this is a reactant. This is grams of sodium bicarb that is used, that has been used in the reaction. So you want to make sure as you're doing these calculations that you connect it back to the physical reality of what's going on with the reaction. So our sodium carbonate, of course, was a product. So that's why that is grams formed. This is a reactant. This is how much we have used. But of course, the question doesn't ask us how much was used. It asks us how much of our reactant is left over. So we are not quite done with this part of the problem yet. We just know how much is used. So what we need to do is we need to figure out how much we started with, subtract how much we used, and that will give us how much is left over. Okay, so we started with 10 grams. This is start. We have used 2.57 grams. So when I subtract these, I get 7.43 grams of my bicarb remaining. Okay, so that is, I think that is the end of the second part. Okay, we've got our partial pressures. We know the grams of bicarb and sodium carbonate when equilibrium is reached, and we've got one more piece. What would the volume of the vessel need to be in order for all 10 grams to decompose? Okay, so obviously we did not decompose all 10 grams because we only had a 1 liter vessel. So the question is, what size do I need to make my reaction vessel so that all of this bicarb will decompose? And then I'm only left with sodium carbonate and carbon dioxide and water. Okay, so we really want to think about doing this problem, but in reverse. So we want this number to be 0. So let's go, let's change color because this is getting a little bit tight here. So if we're going to use all of our grams of sodium bicarb, how many moles of CO2 would that be? So again, you can kind of think of this problem as taking this guy and working all my way back to my moles of CO2. Okay, so there is my grams of sodium bicarb. Let's convert that into moles because we're going to do more stoichiometry, and so we have to be in moles for that. And okay, that is my molar mass. Okay, and using my mole ratio, again, make sure that you're writing down your units because it's very easy to get this flip-flopped. Now, I could, of course, continue on to grams of CO2, but if you remember, we got this moles of CO2. Let me just switch back again because we were using ideal gas law here, and this is what's going to connect us back to our volume. So I don't want to calculate my grams of CO2. I just want to calculate my moles, and I'm going to stay in moles. So if I do this calculation, I get 0.595 moles of CO2. So that is how many moles of CO2 that I want to have at equilibrium, because that means all of my 10 grams of bicarb have decomposed. But of course, it asked me what volume of vessel do I need. So remember how we got our number of moles from our ideal gas law from our total volume here. We knew our total volume was 1 liter. Again, now we're kind of working backwards. We initially used ideal gas law to figure out our total number of moles, but in this case, we already have our number of moles, and we're going to go back and figure out our total volume that we're going to need. Okay, so I have my moles of CO2, but that is not my total number of moles. But if you remember, your mole fraction for CO2 is equal to 0.5, which is equal to my moles of CO2 over my total moles, which is equal to my moles of CO2, which I have 0.595, and that is over my total number of moles, which means my total number of moles is 0.119 moles total. Okay, I've got one more piece here I've got to plug back into ideal gas law. I'm really running out of space here, so I'm going to add in another sheet because I just can't squeeze it in anymore. Okay, good old ideal gas law. But again, remember, this is total pressure, total volume, total number of moles times RT. My total pressure is the same as it was before. So if I go back 2 times, you can see my total pressure I've already calculated is 1 atmosphere. All right, so that is 1 atmosphere. I am trying to figure out what total volume I need, so I'm going to leave that as my variable. I just calculated my total number of moles, which is right down here. So that is 0.119 moles. I want volume. I'll just have volume come out in liters, so I will use the same value for R that I used before because that is liter atmosphere over mole K. Again, it's very frustrating to get these long problems wrong just because of a unit error. I know because I have done that. And then our temperature is still the 125 Celsius, which is 398 Kelvin. All right, so this is going to give us our volume in liters. So if I solve for my total volume, I get 3.89 liters. So for all of that 10 grams to decompose so that I have none of my reactants, none of my bicarb left, I would need a vessel that is almost 4 liters, almost 4 times what I have got right here. Whew, that was a doozy of a problem. Okay, there are no questions. I don't know if that means everybody is lost or that everybody has gotten it. But what is cool to see about this problem, again, just like the last problem, is you have to bring in other aspects of chemistry. It's not just, oh, this is an equilibrium problem and it's all by itself and we don't think about anything else. We had to also bring in ideal gas law and Dalton's law of partial pressures and our stoichiometry as well. So it's nice when you have these synthesis problems because it really helps bring together all of these different concepts that you have. And when you can put them all together and figure out a problem like this, then it means you really do understand what is going on. And I find it very satisfying. Hopefully you find it very satisfying as well. Okay. That was our second problem. But don't worry, I only have one more because I knew that second problem was going to be a bit of a doozy. So let's go on to our last problem. Sulfur dioxide is removed from smokestacks by the following equation. Okay, so we're using calcium oxide to scrub out sulfur dioxide. Okay, so I'm sorry, there's an error in this one too. There should be equilibrium arrows right there. All right, I need to be more careful about proofreading my problem. Sorry about that. All right, so the delta G of this reaction is negative 418.6 kilojoules. What is the pressure of SO2 in the smokestack after it has achieved equilibrium according to the above reaction? Assume the reaction takes place in the air where the partial pressure of O2 is 0.21 atmospheres. Okay, so this is not like in a sealed vessel like in the last problem. This is just in the atmosphere here, but they did at least give us the partial pressure of O2 in the atmosphere, which is helpful. All right, this is another synthesis problem because we have a delta G here and we've got an equilibrium problem. So at some point we're going to have a K. And because I'm dealing with gases here, it's going to be a Kp. All right, so let's first take a look at our delta G because I know I can put together delta G and K. They do have a mathematical relationship. All right, so that mathematical relationship is K, and in this case it's going to be a Kp because we're dealing with gases. So we've got a pressure is equal to E to the negative delta G over RT. All right, the nice thing about this is we are going to be able to do this and we're going to be able to find our Kp from our delta G. All right, so let's plug and chug and let's actually get our Kp. All right, so this is E to our negative and our delta G is negative 418.6. Now that just says kilojoules, but because we've got a 1-to-1 ratio here, that is actually kilojoules per mole. All right, great. This is over RT. Now I want to be, again, careful here and choose the value of R that's going to match. So I don't want to choose the value of R that I did for the last problem because that's liters atmospheres over mole K. And while I do need to have the K because I've got a T, I do not have liter atmosphere. So instead, I want to use a different value for R, and I want to use this one right here, 8.314, because that is joules per mole K. And then my temperature. So my problem, again, does not specifically state my temperature, but because this is standard state, I know that this is occurring at 25 degrees Celsius, which is 298 K. All right, before we can actually put this in our calculator, we do have a problem that we have to deal with. And it is this. My Kelvin is going to cancel, no problem. My moles are going to cancel, no problem. But look, I've got joules and I've got kilojoules. So close with the units, but not quite. So let me fix that. And I am just going to take this kilojoules and turn it into joules. Of course, you can always do the other way around, no problem. So this is going to be negative 4. And so I'm just multiplying by 1,000. So that is now joules per mole. And my denominator stays the same. Joules per mole K. And this is 298. Okay, so just double check. We've got joules, we've got moles, we've got Kelvin. Okay, great. All of our units cancel, which is exactly what we want. So if you plug this into your calculator, you will get a value of Kp of 2.38 times 10 to the 73rd. That is massive. That is like beyond massive. That's just huge. It's to the 73. Oh my goodness. Okay. So just think about this physically for a second. When K is so large, what that means is, in essence, this reaction goes to completion. I wouldn't even put equilibrium arrows knowing that my Kp is so large. I would just say it's one way to the right. So as I figure out what the equilibrium pressure of SO2 is, before I even do any math, I'm already thinking, all right, basically, this is a right-hand arrow only because my Kp is just so huge. So I would expect my pressure of SO2 should be very, very, very tiny, should in essence be 0. Now we'll be able to actually calculate something, but that is what I am expecting because again, my K is so large for this. And that's good because if we're trying to scrub out sulfur dioxide, then in essence we want its partial pressure to be 0 once all of that gas from whatever that plant is, once it's been gone through the scrubber and released into the atmosphere, we want no SO2 in it anyway. So that's a good thing, but this is what my expectation is, so that as I work through the problem, that the numbers follow what logically I think should happen. It's always nice to have those little checks, because if I get a massive equilibrium pressure of SO2, then that doesn't make sense with what my value of K is. Okay, with that being said, let's actually calculate what's going on. So let's rewrite my, well, actually, maybe let's just go ahead and write my Kp here. So my Kp is going to be really easy because, again, I don't mess with my solids. So this is going to be 1 over pressure of my SO2 times the pressure of my O2, and because I have a 1/2, that is raised to the 1/2. That one is really a little bit messed up. Okay. And just as a reminder, when something is raised to a fraction, it means it's a radical. So when something is raised to the 1/2, it means it's a square root. If it was raised to the 1/3, it'd be a cube root, et cetera, et cetera, et cetera, et cetera. All right, and the reason why I jumped straight to the Kp and I'm not doing an ice table is because I know what the pressure of O2 is. It's 0.21 atmosphere, and I know what my Kp is. So I can just plug and chug, and I'll calculate my pressure of SO2. So plugging in my value for Kp, my massive value for Kp times 10 to the 73rd is equal to 1 over my pressure of SO2, which is what I'm calculating. My pressure of O2 is 0.21. That is raised to the 1/2. All right, so if I solve this for my pressure of SO2, which again is just a little bit of algebra, then I get 9.2 times 10 to the negative 74th atmospheres. All right, again, remember how we said we assumed that the pressure of SO2, the equilibrium pressure of SO2, should be basically 0. I would call this basically 0. 9.2 times 10 to the negative 74. You're going to have to put 73 zeros in front of that 9 to get to that pressure. So again, my equilibrium pressure matches with what I got for my equilibrium constant. And in this case, this is exactly what you would want in a scrubber for a smokestack. Okay, so that is it for all of my heterogeneous equilibrium problems for tonight. As always, send me or leave me a comment on YouTube or Facebook and let me know if you have any requests for topics for future live streams, or even if you want me to help you work a certain problem. That's fine. I just need to know by say Tuesday afternoon if you have a certain problem that you'd like help working through. And I hope you enjoyed this live stream, and I hope you found it helpful. Thanks so much for joining us. Bye.